SpaER, a pioneering method for fetal motion tracking, leverages equivariant filters and self-attention mechanisms to learn spatio-temporal representations. Conventional approaches statically estimate fetal brain motions from pairs of images, whereas SpaER dynamically tracks rigid movement patterns across temporal and spatial dimensions. The method first develops an equivariant neural network that efficiently learns rigid motion sequences through low-dimensional spatial representations of images. Subsequently, it learns spatio-temporal representations by incorporating time encoding and self-attention neural network layers. This approach captures long-term dependencies of fetal brain motion and addresses alignment errors due to contrast changes and severe motion artifacts. The model provides a geometric deformation estimation that properly addresses image distortions among all time frames. Unlike existing methods, SpaER learns spatial-temporal representations via deep neural networks for fetal motion tracking without data augmentation. It has been validated using real fetal echo-planar images with simulated and real motions. Fetal motion tracking faces challenges due to complex fetal movements, discrepancies among data frames, and local geometric distortions. Existing techniques, including slice-to-volume reconstruction, have limitations in capturing large and rapid fetal movements. Spatio-temporal representations have been utilized for in utero image tasks, but they require iterative optimization processes, rendering them impractical for real-time motion monitoring tasks. Deep learning approaches have improved model performance in motion estimation. Methods predicting 3D rigid transformations and real-time fetal motion tracking using various designs of deep neural networks have been introduced. However, these methods still encounter difficulties in capturing true spatial-temporal relationships due to their fixed image context range and susceptibility to unpredictable motions and distortions. SpaER's core contributions include being the first predictive approach in dynamically learning fetal brain movements spatio-temporally through deep equivariant representations without data augmentation, outperforming state-of-the-art methods in motion tracking accuracy, and ensuring stable convergence of training and fast inference. This feature holds significant clinical value, particularly for on-scanner quality assurance and prospective acquisition planning. The research paper presents a novel approach for real-time fetal head motion tracking, utilizing deep neural networks to learn spatio-temporal representations. This approach, named SpaER, is designed to efficiently estimate rigid transformations between image pairs without requiring network retraining for unseen image modalities. The methodology builds upon recent work by Moyer et al., which uses equivariant filters to accurately estimate rigid transformations between pairs of images. The paper first reviews the concept of rigid motion estimation via equivariant filters, where the goal is to identify the best translation and rotation parameters that define a rigid transformation. This is achieved by minimizing the distance between the transformed source image and the target image. The authors then introduce their approach for spatio-temporal sequence estimation of rigid transformations, focusing on learning spatio-temporal representations. The proposed model architecture consists of 3 submodules: a boosted rigid motion correction neural network parameterized by equivariant filters, a temporal encoding module that incorporates time information into the equivariant features, and a self-attention neural network that learns feature correspondence across different time points. The network is designed to capture rotation equivariant representations through the use of 3D steerable CNNs. The authors also detail the process of spatio-temporal encoding, which maps time information of the input sequence to image features. This is achieved using a positional embedding matrix, where each element on the TTH position is calculated using sine and cosine functions of the time variable. The paper concludes by highlighting the potential of SpaER for efficient fetal motion tracking in real time, automated fetal head motion tracking, and prospective steering systems. The proposed approach offers a theoretical framework that lays the groundwork for rigid motion estimation without the need for network retraining for unseen image modalities. The SpaER framework efficiently tracks fetal motion by learning spatio-temporal equivariant representations. It integrates temporal features with spatial means through self-attention, enhancing the closed-form solution for image alignment. The geometric deformation correction module addresses local distortions using a diffeomorphic deformation estimation model. The total loss for network training combines both losses with a weighting factor for balancing contributions. The framework's performance is evaluated on a dataset of 240 sequences from 15 subjects, comparing favorably with static learning-based motion correction methods. The results, presented in Table 1, show SpaER's superiority in motion correction errors for both translational and angular measures. The effectiveness and stability of SpaER are highlighted through a dice coefficient analysis, assessing alignment accuracy across varying motion degrees and sequence lengths. The code is released online for further exploration. The SpaER method, presented in this research, efficiently tracks fetal motion by adopting a spatio-temporal equivariant representation learning approach. This differs from existing methods, which focus on estimating motion parameters at individual time frames. The SpaER method achieves the lowest errors in motion tracking, with an average movement error of approximately 3.8 mm for the fetal brain, and exhibits the lowest variance between adjacent 3D volumes. This is demonstrated through case studies and quantitative comparisons in tables and figures. The method's efficiency is further highlighted by its ability to handle varying degrees of motion and data sequence lengths, including real fMRI scans with simulated motions. The average time consumption for motion tracking is 10 seconds for a 4D sequence, making it suitable for real-time tracking. The SpaER method's effectiveness in correcting rigid motions and geometric distortions is visually demonstrated through the alignment results of two representative cases, showcasing the best motion tracking accuracy among compared methods. Here is a combined summary of the 2 pages. The SpaER framework, a novel approach for efficient fetal motion tracking, integrates time information into low-dimensional spatial means of image data. This framework excels in achieving the best and most stable performance across unpredictable fetal motions and excessive movement of fetuses, showcasing great potential in real-time tracking and steering for fetal head monitoring systems. The authors acknowledge the support of various institutions, including the National Institute of Biomedical Imaging and Bioengineering, the National Institute of Neurological Disorders and Stroke, and Eunice Kennedy Shriver National Institute of Child Health and Human Development of the National Institutes of Health, as well as NVIDIA Corporation. The paper references various works on diffeomorphic image registration, including log Euclidean frameworks, symmetric diffeomorphic image registration, and voxel morph. It also cites research on group equivariant convolutional networks, keypoint detection, and deep learning frameworks for fetal brain segmentation and motion correction. The authors provide an extensive list of references, including works on spatio-temporal MRI atlas of the fetal brain, automated fetal brain segmentation, motion correction of multi-slice MRI, and temporal registration in initero-volumetric MRI time series. Additionally, the paper references research on 3D pose regression using convolutional neural networks, motion compensation techniques in neonatal and fetal MRI, and motion-robust diffusion compartment imaging using simultaneous multi-slice acquisition. The authors also cite works on equivariant filters for efficient tracking in 3D imaging, real-time deep pose estimation with geodesic loss, and deep predictive motion tracking in magnetic resonance imaging. Finally, the paper references research on spatio-temporal motion correction and iterative reconstruction of initero-fetal fMRI, efficient total variation algorithms for super-resolution in fetal brain MRI, and spatio-temporal alignment of initero-BOLD MRI series. SpaER. Efficient fetal motion tracking 11. The paper presents a comprehensive overview of various methodologies and algorithms used in fetal motion tracking, focusing on the SpaER method. It begins by discussing the importance of motion tracking in fetal imaging, highlighting its role in improving image quality and diagnostic accuracy. The authors then delve into the concept of attention-based neural networks, citing Vaswani et al.'s work on Attention is All You Need, 2017. This is followed by an exploration of metamorphic image transformations, as described by Wang et al. in their paper on Metamorph, 2023. The discussion also covers geometric shapes in deep image classifiers, referencing Wang and Zhang's GeoSH model, 2022. The paper further discusses rotationally equivariant features in volumetric data, as proposed by Weiler et al. in their work on 3D steerable CNNs, 2018. Additionally, it touches upon multimodal volume registration through maximization of mutual information, a technique introduced by Wells et al., 1996. In the context of MRI, the authors mention real-time perspective motion correction using image-based tracking, as developed by White et al. in their Promo method, 2010. They also discuss implicit neural representation for slice-to-volume reconstruction in MRI, referencing Xu et al.'s NESVOR model, 2023. The paper concludes with a discussion on iterative transformer for slice-to-volume registration in fetal brain MRI, as presented by Xu et al. in their SVORT method, 2022, and 3D fetal pose estimation with adaptive variance and conditional generative adversarial network, introduced by Xu et al. in their work on 3D fetal pose estimation, 2020.